So we're ready to start? Yeah. Yeah?
Yes, we do.
Okay. So it's beholden to me to chair this meeting. So hello, everybody. And Alex provided me with some vital statistics. So I'd like to welcome Alexei Maznev, who's now at MIT. Warmly welcome Alexei Maznev. And let me say just very briefly that he's originally from the Moscow Institute of Physics and Technology, where he got physics degree and diploma, if you like, and a PhD from the General Physics Institute of the Russian Academy of Sciences with a thesis on laser-generated surface acoustic waves, including the first experimental observation of surface phonon focusing. Then he held a postdoctoral positions at the Freie Universität Berlin as an Alexander von Humboldt Fellow, and also at MIT, where he developed an optical heterodyning scheme for laser-induced transient and grating experiments, which are currently used in many laboratories around the world, including a spell in our lab. And subsequently, he worked as an industrial researcher, mainly at Philips Electronics, North America, developing metrology systems for the semiconductor industry using optical and optoacoustic techniques, before returning to MIT as a staff scientist. So his current interests involve a broad range of topics pertaining to wave propagation phenomena, primarily in acoustics and related fields such as phonon-mediated heat transport on the micro or nanoscales. And he's collaborating now with many groups around the world. I have also the privilege of being one of those people. And he's held visiting positions at the Université du Maine in France, which is now known as the Le Mans University, and Hokkaido University, as I mentioned, the University of Witwatersrand in South Africa, and the University of Heidelberg in Germany. So if you did check the recent journals, you will see Alex is there with extreme ultraviolet experiments for generation of surface waves, and not so long ago, a paper in Science where they discovered second sound in graphite. So things are going really swimmingly for Alex at the moment. So it's with great pleasure that we can welcome Alex today to talk about this very long titled talk, which I think I'll leave Alex to talk about. Okay, Alex?
Okay.
Because I don't want to waste your time by repeating the title. So go ahead.
All right, Oliver. Thank you. Thank you for the introduction, and thank you the organizers for inviting me to talk in a metamaterials seminar series. This is especially generous of you, considering that my talk is explicitly not about metamaterials. So I won't even, read the title for you. I'll just start. So basically, the development of ideas and the physics of classical waves in the last few decades followed a pattern where something was first discovered in optics and then reproduced in acoustics. So like, the photonic crystals came first, then phononic crystals, and then optical metamaterials were followed by acoustic metamaterials. And now, of course, this has not always been the case. For example, whispering gallery modes were discovered by Rayleigh first with acoustic waves and then found applications in optics. And of course, even in the recent research, you can find a number of nice original results obtained in acoustics. But now, a peculiar thing is that there are a number of phenomena which in acoustics had been well known and observed with regular materials, but were then rediscovered in the context of photonic crystals and optical metamaterials, and then even reproduced with acoustical metamaterials and phononic crystals. And this is what I'm going to talk about today. So basically, I'm going to describe some examples, three phenomena, or three classes of phenomena. First, so-called self-collimation of waves, and that was observed in photonic and phononic crystals, but can also be observed without any periodic structures in acoustics. Next, negative group velocity, negative refraction, Veselaga lens, and Dirac cones. Again, mostly, researched in the context of metamaterials and photonic crystals, but can be observed without them. And finally, so-called embedded states in the radiation continuum. So this will be mostly historical and didactical, with some bits of more recent research. Okay, so self-collimation. Self-collimation is a phenomenon discovered first with under this name. Discovered with photonic crystals, then reproduced with phononic crystals. And what it is that in certain directions in a photonic or phononic crystal, a beam of light or sound can propagate without diffraction, as shown here. But now in acoustics, this phenomenon has been known for a long time before even the term photonic crystal has been coined. And in particular, it was observed with surface acoustic waves in certain directions on crystal surfaces. And this is our old experiment where we visualize this phenomenon by using micron-sized particles spread on the surface. So here is a germanium 111 crystal surface. The light scattering comes from these particles, therefore the surface looks light. And then we focus laser in a line here, and then the surface acoustic wave propagates from our source. It's sort of a planar wave, but with a limited aperture. Therefore, there is diffraction. And everything's the same in both images. The only thing that is different is the propagation direction. And as you see here, on the top view, there is a significant diffraction. So basically, the dark area is where surface wave ejected the particles. So it shakes the particles off the surface as it propagates. So we can sort of visualize the surface acoustic wave beam, so to speak. And you can see significant diffraction at the top image and virtually no diffraction in the bottom image. Nothing is different, just the propagation direction. Now, the reason for this phenomenon is the deviation of the group velocity direction from that of the phase velocity in anisotropic media. So you see, the reason that we have diffraction is that the field we excite contains a spread of wave vector directions, which then in the far field translates in the angular spread of the acoustical or optical intensity. But this is assuming that the energy propagates in the wave vector direction, which in anisotropic media is not true. In fact, the energy propagates in the direction of the group velocity, and the group velocity is a gradient of frequency in the wave vector space. So if we plot here isofrequency contours in the wave vector space, here's a section of this isofrequency surface for silicon. So here's the longitudinal waves, slow and fast transverse waves, They are also called slowness surfaces in acoustics. And then group velocity will be orthogonal to these isofrequency surfaces. So now it turns out that the isofrequency surfaces for transverse waves may have points of zero curvature. And at these zero curvature points, all group velocity vectors point into the same direction. That is, at this point, the diffraction should be suppressed, right? Because for a finite range of wave vectors, we have the same group velocity direction. So there will be no angular spread of energy. So that's what's causing this phenomenon. And the consequences of this effect are even more spectacular if you have a point source. Because if you have a point source, then it turns out that in the far field, you have singularities in the angular distribution of intensity. So this has also been observed, or I'm not sure observed, but certainly theoretically discovered with photonic crystals not so long ago. But in acoustics, this is also a well-known phenomenon, which has been originally observed, interestingly, not in a conventional acoustic experiment, but with thermal ballistic phonons in a so-called heat pulse experiment, where you have a crystal cooled down to liquid helium temperature, and then you have a heat source on one side, and you place a bolometer on the other side and look at the distribution of the heat flux. Now, in a good quality crystal, the thermal phonons propagate without scattering. So basically, the heat propagates as acoustic waves. And what they found is that on the backside of the crystal, you have strongly anisotropic distribution of intensity with very sharp maxima. So that's this phenomenon that was termed at that time phonon focusing. So this is basically the same as this self-collimation effect. So the singularities in the intensity propagation from point source. Now, there is an easier way to observe it in acoustics without cooling things down to liquid helium temperature. And we observed it very easily with surface acoustic waves using the same visualization techniques with the micron-sized particles. So basically, we just take crystal surface, we focus laser in a small spot, then surface acoustic waves propagate away from this point source, and then we see this, beautiful, strongly anisotropic pattern. Again, so the black lines, dark lines correspond to maxima of surface acoustic wave intensity, and you can see extremely sharp maxima. Now, interestingly, when this happens, the group velocity surface, wave surface, or in other words, the wavefront propagating from the point source acquires cuspidal features. So you see in an isotropic material, the wavefront is a circle or a sphere in 3 dimensions. And you would think that in an isotropic material, the sphere would be somehow deformed, but it's not just deformed. It's really acquiring self-intersections and cuspidal features. And these cuspidal features in the wave surface could also be directly measured. And the cusps here correspond to the maxima of intensity observed in our images. So these are acoustic caustics in the propagation from point sources in anisotropic materials.
Alex, aren't you putting powder on the surface here?
And this image, say it again.
You sprinkled powder on the surface?
Yes, that's it.
What powder is it?
So those were alumina particles, a few microns in size. And finally, surface acoustic wave propagation in a strongly anisotropic material telluride visualized by our eminent chairman himself in his group. So here the laser pulses strike at the center periodically with a 12 nanosecond interval, and you see this strongly anisotropic pattern of surface waves propagating from this point. So this is amazingly experimental data, not a simulation. Okay, so let's go to our next topic, negative group velocity. So negative group velocity, of course, happens in negative index metamaterials, but you don't need a negative index to have negative group velocity. And I believe the first person who noted that negative group velocity may occur in mechanical systems was Lamb. And I'm going to talk about negative group velocity of Lamb waves, which were discovered by Lamb, but the systems that he considered were not Lamb waves. So it was actually later found that Lamb waves exhibit negative group velocity. This is a typical dispersion of Lamb waves in an elastic plate. So this is aluminum, but you will see similar dispersion curves in many materials. And you can see that the second order symmetric dispersion branch here has a section with the negative slope of frequency versus wave vector, which indicates negative group velocity, or you can say negative phase velocity at any rate. So that the energy propagation direction is opposite to the wave vector. Now, this has also been observed in other systems. Here's one example, our work on surface acoustic wave and a light system where similar negative group velocity effect was observed even in the fundamental acoustic mode of the system. And when this happens, when you have waves with negative group velocity, then you can have a situation where you have an interface between two media, which is in the case of Lamb waves can be very easily realized by making a thickness step. So basically, we have the boundary between plates of different thickness. And if you have a mode conversion between a wave with positive group velocity and a wave with a negative group velocity, you ought to have negative refraction. And if you find a point where the branch with a positive group velocity on one side of the interface intersects with the branch of the negative group velocity on the other side of the interface, you ought to have the so-called Vesselaga lens condition. That is a point source placed on one side of the interface will be perfectly imaged by this interface on the other side. And this has indeed been experimentally observed by my collaborators, a group headed by Todd Murray. Now, this is, of course, not a super lens. The focusing is still diffraction limited. So you see, this is a Vesselago lens. This is the super lens discovered by Pendry, is only working in the near field. And it can indeed deliver focusing into a spot much smaller than half lambda. A Vesselaga lens, on the other hand, works in the far field, but it is diffraction limited. It just so happens that a slab of negative index material is simultaneously a Vesselaga lens and a super lens, but this is generally not the case. This is a Vesselaga lens, but not a super lens. Okay. Now, if we back to these dispersion curves. So if we go to the gamma point, zero wave vector, then the Lamb modes of an elastic plate at the zero wave vector point correspond to thickness resonances of the plate. These thickness resonances, they occur for longitudinal and transverse waves, and they don't interact. So basically, these are just sort of thickness resonances. Basically, certain number of wavelengths fits into the film, into the thickness of the plate. They start interacting when the wave vector becomes non-zero, and that's actually why this negative group velocity occurs. This is basically a level repulsion caused by this interaction. But exactly at zero wave vector, there is no interaction, so they're independent. So it may so happen that the longitudinal velocity is exactly 2 times larger than the transverse velocity, and then the second order transverse thickness resonance will exactly coincide with the first order longitudinal resonance. So then we have a crossing at this point, and then we have a cone, because this is isotropic, this is a plane. So if we have a crossing point, this will be a conical point in 2 dimensions. So it will be a Dirac cone. All we need for that is a material with Poisson's ratio equal exactly 1/3, or the transverse to longitudinal velocity ratio equal to 0.5. This is for a free plate, or for a plate which is clamped on one side, the ratio should be 1/3. So again, that's and this has been noted by Mindlin as early as 1955. You see, Dirac cone without phononic or photonic crystals. It was then more recently rediscovered in the context of photonic and phononic crystals research. Basically, similar phenomenon of Dirac-like cones, they say, occurring at the gamma point in these artificial materials. Now, an experiment what people have done, they found an aluminum alloy where this velocity ratio was extremely close to 1/2, and then they cooled it down additionally to get exactly this 1/2 ratio, and they observed a number of interesting phenomena that happen when you have this Dirac cone dispersion. Another thing you could do is that you can have a bilayer system. You can add deposit a thin layer on your slab, and then you can tune the dispersion by varying the thickness of one of the layers. So you can bring it to this degeneracy point, and then I think you can consider interesting possibilities. For example, you can deposit a layer with variable thickness, and then you can generate your wave somewhere at a finite wave vector and bring it adiabatically into this Dirac point. So there has not been any experiment yet, but I think there are some interesting possibilities for studying this phenomena with these conventional simple layered systems. All right, now let's go to my third topic, and this is embedded states in the radiation continuum, or bound states in continuum, a phenomenon first suggested by Wigner and von Neumann in quantum mechanical systems, but never observed for the systems that they discussed. However, it was observed later with classical waves. And in particular, this paper by my MIT colleagues presented the bound state in continuum in a photonic crystal slab. And this paper basically started an explosion of activity in this field. Was followed by a great number of papers, both in optics and acoustics, on embedded states in continuum. So basically, what happens here is that the true waveguide modes normally should be slower. Let's say a waveguide mode of a slab in a dielectric slab should be slower than the velocity of light in the surrounding medium, because otherwise this mode will radiate into the surrounding, and it won't be a true waveguide mode. It will be a so-called leaky mode. So if you look at the dispersion of waves in a photonic crystal slab, you'll see that this green area is the light cone. So whatever is below the light cone is true guided waves here. But inside the light cone, they become leaky. So they are not true waveguide modes. They radiate, they lose energy. But it turns out that there are some isolated points within this radiation continuum. And in these isolated points, just accidentally, radiation vanishes. Well, in fact, sometimes there are these the points protected by symmetry. So, for example, if you have if the waveguide mode has a different symmetry than the wave that would be radiated in the surrounding, then it does not radiate. And but this is trivial. So this has been known. So what they observed is not symmetry protected bound state and continuum, which they call BICS, totally accidental. However, they're structurally stable. So when the parameters are changed, this point might travel up and down the dispersion curve, but it stays there. And they claim that this was the first experimental observation of this robust non-symmetry protected bound state and continuum. And curiously, while they were making this discovery, these non-symmetry protected bound state and continuum were already used in their cell phones. You see, in acoustics, this phenomenon has been very well known for years or decades. This is indeed happening with surface acoustic waves without phononic crystals in conventional materials. So here I show the angle dependence of surface acoustic wave velocity on the basal plane of gallium arsenide from this paper by Stegeman. And you see in isotropic materials, surface acoustic wave velocity is always below the bulk wave velocity, just like for regular waveguide modes. But in anisotropic materials and crystals, it turns out there are branches of surface wave-like modes, which are faster than the slow transverse wave. They are leaky waves. They're not true surface waves, so they radiate energy into the bulk. But it turns out that within these branches, there are, again, isolated directions where they don't radiate, and they turn into the true surface modes. Some of these isolated directions are symmetry protected. So, for example, here in the 110 direction, this leaky surface wave is polarized in the sagittal plane, whereas the slow transverse wave is shear horizontal. So they're decoupled by symmetry. That is, this leaky mode cannot radiate into the slow transverse wave, and because of that, it becomes the true surface wave here. This is a symmetry protected direction. But then Stegeman found that there is an inconspicuous direction elsewhere, where again the radiation loss disappears. So this is this non-symmetry protected bound state and continuum. Now, even more interestingly, simultaneously, people who were studying surface acoustic wave devices found that within these and surface acoustic wave devices mostly use lithium niobate or lithium tantalate. And they looked into these leaky branches of surface acoustic waves in these materials and found that depending on the orientation of the surface, for some surface orientations, the losses are minimized. And again, so this sort of or really disappear. So these points where the radiation loss disappears correspond to bound states in continuum. And this is exactly what is used in the surface acoustic wave filters used in cell phones. For some reasons that I don't quite understand, they like these leaky surface acoustic waves more than conventional surface acoustic waves, not just because they are bound states in continuum, they don't care, but other parameters are better. So the velocities are larger than for the regular surface waves. Also, the electromechanical coupling coefficients are larger, so they like them. And simultaneously, if they can minimize the radiation loss, it turns out that these waves work better for the SAW devices than regular conventional slow surface acoustic waves. So that's actually the kinds of waves that are used in SAW filters and resonators in cell phones and other similar devices. Now, so these are anisotropic materials, acoustically anisotropic materials, and this has been all well known for decades. Now, Arthur Avery and I asked ourselves, can this happen in elastically isotropic materials, in lead structures? We know that in an elastic half space, this cannot happen because there is the only surface acoustic wave velocity. This is always below the transverse velocity. But if we, let's say, consider a layer, elastic layer on a substrate, or a multi-layer system, or let's say half space or a lead structure loaded by liquid, so can this happen without elastic anisotropy? So we considered several classes of systems, and for some of them we proved that this bound state and continuum cannot exist. In other cases, we actually found examples showing that they do exist. So first I show you an example of non-existence proof. For example, supersonic, the love waves, which are guided waves which are transversely horizontally polarized. We showed that for the waves of this kind, there cannot be a guided mode which is faster than the transverse velocity of the substrate. The reason being that if it existed, then the field and the substrate would have to be identically zero, because otherwise there would be a radiated wave. But if it's zero in the substrate, then you can also prove it's zero. It is zero in the next layer, and then the next layer, and the next layer, and then it's zero everywhere. And by the way, the same proof works for optics. Also in optics, these bound states and continuum cannot occur in isotropic layered systems. However, so these are for the shear horizontal waves. However, if in the same layered systems we consider Rayleigh-Lamb waves, which are polarized in the sagittal plane, then the situation is different, because in this case, if you have a mode whose velocity is between transverse and longitudinal bulk velocity, then there could be an evanescent longitudinal wave in the substrate. So the field in the substrate doesn't have to be zero, even if if this mode does not radiate. So in this case, that is, there is a possibility for this non-radiating mode, which is faster than the transverse velocity, to occur. But then, in order to prove that this happens, you need an example. And in fact, we started looking, and we found that they're very common. So basically, you take a very common, lead structure, the simple lead structure here, a gold film on a fused silica, and these are the dispersion curves. So here is the transverse velocity. So below the transverse velocity, we have a conventional guided waves, conventional guided modes. So above the transverse velocity, instead of plotting the velocity, we're plotting the imaginary part of the Green's function. And essentially, it shows resonances of the finite width. And so basically, the width of the line shows the width of the resonance, and the width of the resonance shows how much this wave radiates into the substrate. So these are all leaky branches. So the fact that they are finite width resonances indicates that they're leaky. So below the transverse threshold, these resonances become delta functions. So they're not leaky anymore. So these are infinitely narrow resonances. But now it turns out that within the leaky branches, there are multiple isolated points where the resonances again become infinitely narrow. The radiation disappears, and we showed that. We showed that, for example, as you go through through this point, the phase jumps by 180 degrees. That is the sign of the radiating field changes sign. That is, it must go through zero. Also, if you look at the structure of the field, the displacement pattern, you can see that elsewhere within this leaky branch, you clearly see this radiated wave radiated into the substrate, but at this embedded state point, you basically clearly see pattern where the energy is concentrated near the surface. Now, another interesting example is fluid-loaded solid systems. In this case, and normally, if you have a substrate and fluid above it, and you have a surface acoustic wave, normally the acoustic wave velocity in a solid are larger. So commonly, surface acoustic wave will radiate energy and to the fluid and become leaky. Now, there is, however, one case when it won't radiate, and this is when the vertical displacement component of this wave at the surface is zero. That is, if the displacement at the surface is horizontal, then there will be no radiation because it will not couple to the bulk wave on the liquid. So this is peculiarity of acoustics, and in optics this does not happen. So this is a peculiarity of a solid-liquid interface. You may have a wave in a solid, and if the displacement of the surface is horizontal, then it won't couple to the liquid. And of course, one trivial example is shear horizontal wave or love waves, if we're talking about guided waves. But this is an example of so-called symmetry-protected embedded states. So of course, they don't couple to the liquid. But now, how about Rayleigh waves? So Rayleigh waves on an isotropic half space, the Rayleigh waves are elliptically polarized, as we know. And the ellipticity, that is horizontal to vertical ratio, is basically within 0.5 and 0.8. So they're always elliptical. So the polarization can never become pure vertical or pure horizontal. However, if you deposit a layer of different elastic properties on the substrate, it turns out that this may happen, and it's been known that it may happen. That is, depending on the layer thickness, the polarization may become either horizontal or vertical. And if it becomes horizontal, then this guided mode will not couple to the liquid above and will not radiate. And indeed, we considered a system of a polymer layer on a silica substrate. And here the dispersion curves, and the colors basically denote the polarization. So it's not circular, it's actually elliptical. I just schematically shown the direction. So it's either counterclockwise or clockwise, and there are transition points between counterclockwise and clockwise direction of motion at the surface. And at these points, the polarization is either horizontal or vertical. And now, at the points where the polarization is horizontal at the surface, we expect that if we add liquid, nothing will happen. Everywhere else, these modes will start radiating and turn into leaky waves. But at these isolated points, where polarization is purely horizontal, nothing will happen. And indeed, this is found to be the case. So here we add fluid and calculate our dispersion. And now, instead of curves, we will have resonances of finite width. But at these isolated points, the loss goes to zero, and they become pure non-radiating waveguide modes. And another consequence of these is that these points are stationary. So basically, you change properties of the fluid, and these dispersion curve will change. And here's an example where originally two dispersion branches bifurcate and turn into a single branch as we increase the fluid density, but these points remain stationary. So basically, the dispersion curves remain anchored at these points where no radiation no coupling to the fluid happens. All right. So how are we doing on time? Do I have another 13 minutes? I have a bonus topic.
Yeah, you have plenty of time. Go ahead.
Okay, excellent. So now this bonus topic does not exactly follow this pattern. So this is not a phenomenon that was well known in acoustics before it was discovered with photonic crystals and metamaterials. But this it still sort of follows this general trend in that this is a phenomenon of active current interest, which has been actively investigated during the past maybe 7 years. And nonetheless, it happens in a classical system, which has been, known for a century in the Lorentz oscillator, and the so-called Lorentz oscillator model. So exceptional points, I'm going to talk about the exceptional points of non-Hermitian operators. So these exceptional points occur in non-conservative systems. And what they are degeneracy points where both eigenvalues and eigenvectors coalesce. So they're different from more commonly known degeneracy points in conservative systems, and that eigenvectors also coalesce in one. So these are well known in mathematics. In application to physics, this whole area has been almost single-handedly developed by Dieter Heiss from scientists from South Africa. But one of a sudden, there was just an explosion of interest within the past maybe 5-6 years with a number of very high-profile papers. But I just want to basically make an observation that this phenomenon happens in a very simple Lorentz oscillator dispersion model, where an electronic state is considered as a classical, essentially classical mass spring oscillator. So this is this, dispersion equation in the Lorentz oscillator theory, and this is of course in optics, but the same equation can be derived for so-called locally resonant acoustic metamaterials. For example, if you disperse resonators consisting of a heavy mass in a shell, disperse them in a medium, and then in the effective medium, within the effective medium approximation, derive the dispersion equation for the longitudinal waves in this medium, you end up with an equation which is identical to the Lorentz oscillator and dispersion equation. Now, let us make this equation dimensionless by setting the frequency of the oscillators to unity and the speed of light of sound to unity, and let's investigate the behavior. So basically, you see this is the product of two terms, and one term describes the dispersion of light or sound in the medium. Another term basically describes the oscillator, and the right-hand side describes the coupling. That is, beta is basically the coupling strength. If there is no coupling, there would be just two lines that cross. The horizontal line, the fixed resonant frequency for the oscillator, and the line with the constant slope for the wave. Now, if you have coupling, then let's first consider a system where there is no damping, no losses. Then there is this classic avoided crossing picture where instead of two crossing lines, you have hybridized modes. And this is totally ubiquitous, occurs in many systems. This is just one example, an experiment that we have done, where we observed the interaction of surface acoustic waves with a monolayer of microspheres. Here, the resonator is the mass spring resonance of the microsphere, that where the role of the spring is played by the Hertzian contact between the sphere and the substrate. And instead of the Rayleigh wave that we had in a system without spheres, we have these two branches. The dispersion equation is a little bit different, but you can show that the actual avoided crossing is described by the same type of equation as the Lorentz oscillator dispersion mode. Okay, so now let's consider a system with damping. So I fixed the oscillator strength and I change damping, and now we have a choice. When we have damping, we can either consider the frequency as a real independent variable and calculate the complex wave vector as a function of frequency. Or we can treat the wave vector as a real and independent variable and calculate complex frequency as a function of the wave vector. So it turns out that the results are not identical. It is only in the case of no damping that they are identical. So here I'm showing the calculation of complex frequency as a function of the real wave vector. And we can see that we start with weak damping, and we see this dispersion brand, the avoided crossing pattern. We increase damping, and you see that these dispersion curves develop a kink-like structure. And eventually they bifurcate. And when they bifurcate, both real and imaginary part of the frequency become the same. You can also show that the eigenvectors become identical as well. And after this bifurcation, there is no avoided crossing anymore. So the dispersion curves just simply cross each other. But the imaginary parts no longer cross. So basically, the system decouples in a branch with large damping. And this is the original sort of the oscillator mode, and the propagating wave with low damping. So basically, in this case, there is no avoided crossing, no polarity anymore. And this is the so-called weak coupling limit, where the oscillators only cause an increased absorption near the crossing. That is the transition from the stroke coupling regime, where you have this avoided crossing and a polariton, and the weak coupling regime happens via the bifurcation at an exceptional point. So yeah, you could also derive the analytical expressions describing this exceptional point. Now the question is, why has it not been noted before? Or at any rate, I don't know of whether of any work or any text where it has been noted. If you know something, then please do tell me. But I haven't seen, and I think the reason is that normally in the when Lorentz oscillator mole is discussed, then it is presented in terms of the dependence of the dielectric constant or refractive index on frequency. That is, it is the frequency that is treated as an independent real variable. That is, it is the same as calculating the complex wave vector as a function of the real frequency. And indeed, if we do this, if we take the same equation and calculate the wave vector, the complex wave vector, as a function of a real frequency, here real and imaginary part, then there is no band gap, there are no two branches, this is not happening. So there is a single branch, and this is exactly what we, used to see from the original work by Lorentz. And that's what's in the textbook. And in the imaginary part, we just see, this absorption peak, which simply becomes broader and broader as we increase the damping. And this is what's also observed in the experiment. So here's an example, of ultrasonic locally resonant metamaterial. And that's indeed what's observed. That is, the theory predicts two branches, but you don't see two branches in the experiment. And now, I believe that it's really, this is not just a formal theoretical thing. Whether you want to use a real frequency as an independent variable or a real wave vector, this actually depends on your experimental situation. That is, if you measure transmission of waves through a slab of material, whether it's transmission of a monochromatic wave or a pulse, then you, in fact, impose a real frequency. And you then, but then the wave attenuates inside the material, that is your wave vector, it becomes complex. So this is the situation where the frequency is real and you need to calculate complex wave vector as a function of the real frequency, and then this bifurcation does not happen. But if you make a scattering experiment, for example, brilliant scattering or an elastic X-ray scattering, then you impose a real wave vector. And then you see a resonance in the frequency spectrum, you see a resonance of a finite width, that is your frequency becomes complex. So this is an experimental situation where you need to treat the wave vector as a real independent variable and then calculate the frequency as a complex function of a real wave vector. And this is when this bifurcation at an exceptional point happens. Okay, and well, on this positive note, I would like to conclude, thank my co-authors and collaborators, and thank you for your attention.
Thanks very much, Alex. Thank you. Very nice, profound stuff. So I'm sure there'll be lots of questions, so including from me, but I will open the floor to everyone else first. So please just ask away. Put your camera on and ask a question.